In this video, we'll look at applications of linear equations that involve distance or motion. For both of these examples, we're going to use the formula d equals rt. The d stands for distance, the r stands for the rate, and t stands for time. So you could think about rate as the speed, and the units for the rate should match the units for distance and time. So for example, if the rate is measured in miles per hour, the time will be measured in hours and the distance will be measured in miles. We're going to look at two examples. The first one, an express train and a local train leave Pittsburgh to travel to Washington, D.C. The express train can make the trip in 4 hours and the local train takes 5 hours for the trip. The speed of the express train is 12 miles per hour faster than the speed of the local train. Find the speed of both trains. All right, in order to help us kind of get a sense of what's happening here, I suggest maybe drawing a picture if that is something that is usually helpful. I think having some sort of visual might help you what's going on. I'm also going to give you some tips on how to organize this, which is why you see a table here. All right, so in the picture, I have just made a location for Pittsburgh and Washington, D.C. My express train is leaving Pittsburgh, going to Washington. It takes the express train 4 hours. The local train also going from Pittsburgh to Washington, it's going 5 hours. Now, we weren't told, and it might not look that way by my drawing, but we're imagining these trains are going on the same track. So the distance from Pittsburgh to Washington will be equal for both trains. We were also told that the express train travels 12 miles per hour faster than the local train. The local train makes some stops along the way, so it takes the express train, well, the express train can go a little bit faster. This is, of course, on average. Trains travel at varying speeds, but if you average their speed for the entire trip, that's really what we're focusing on here. All right, so we're going to organize the information in a table. And we're using the formula d equals r times t. Distance equals rate times time. So we could start with the information that we know. We know the time for both trains. We know the express train takes 4 hours. And we know the local train takes 5 hours. So we can fill those values in. We don't know the distance, but we do know the distance for each is the same, so I'm going to leave those blank for now, but that might help us when we're writing our equation. But we do have some information about the rate. We know that the express train travels 12 miles per hour faster than the local. We don't know what the speed of the local train is, so let's let that be our variable. I'm going to just leave it as r for rate, but you could choose any other letter that you want. Since the express train travels 12 miles per hour faster, we can represent that as r plus 12, or 12 plus r. It's addition, so the order doesn't matter. Now this relationship, d equals r times t, means I would need to multiply the rate and the time in order to get the distance. So I'm going to do that for each of the trains. For the express, I have to make sure that I am distributing the 4 times r, and 4 times 12, or I could even just for now write it using parentheses, so 4 times r plus 12. So either distribute it now or use parentheses around the rate. For the local train, I have 5 times r, which is 5r. All right, so we have written expressions for all of the different characteristics of this problem. Now we need to write an equation. This is where the relationship that the distance that each train travels is equal, because we're going from Pittsburgh to Washington. We're on a train, we have the same set of tracks that are going between the two cities. So the fact that the distances are equal allows us to write our equation. I'm going to take the distance for each train and set them equal to each other. So 4 times r plus 12 is equal to 5r. And now I can solve this equation. First, I'll distribute the 4, if I have not already. 4r plus 48 equals 5r. and then I'll isolate the variable. So in this case, I'd like to subtract 4r from both sides. 48 is equal to r. So I have my value for r. Remember that we were trying to find the speed of both trains. Since I have r, I know that that is the speed of the local train. And I could take that r and add 12 to it to get the speed of the express train. So if I add 12 to 48, I have 60. And that's the speed of the express. Let's move on to our second example. Christopher and his parents lived 115 miles apart. They met at a restaurant between their homes to celebrate his mother's birthday. Christopher drove 1.5 hours while his parents drove 1 hour to get to the restaurant. Christopher's average speed was 10 miles per hour faster than his parents' average speed. What were the average speeds of Christopher and of his parents as they drove to the restaurant? So again, one strategy here would be to gather the information in the problem and maybe draw a little diagram or picture as needed. So I have a diagram here. So we have the location of Chris and of his parents. They meet somewhere in between their locations, not necessarily right in the center, we're not told, but somewhere in between. We know the total distance that they live from each other is 115 miles. We also know that Chris travels for 1.5 hours and his parents travel for 1 hour. We were given some information about the rate. We were told that Chris's speed was 10 miles per hour faster than his parents. So once again, I have the distance formula, d equals r times t, and I'm going to set up a table to help me define each of those variables. I'm going to do one for Chris and one for his parents. I like to begin with the information that is given to me directly, so I'm going to fill in the time for each. Chris traveled for 1.5 hours. His parents traveled for 1 hour. Now the rate, we know that Chris's speed was 10 miles per hour faster than his parents. So let's say his parents' speed is r, and that means that Chris's speed is his parents' speed r plus 10 miles per hour faster. Right, and once again, we could fill in the distance for each of the parties by multiplying. So 1.5 times r plus 10. I could distribute that there, or I'll do it when I need to. And then 1 times r is r. Now, in the train example that we had just looked at, the distances were the same for both trains. In this case, that's not the case. We don't know which person traveled the farthest. We could maybe make a guess that Chris might have traveled the farthest because he drove longer, but he also went faster. We don't know that they're exactly at the halfway point either. But what we do know is if they met exactly in the middle of their locations, that whatever distance the parents traveled and whatever distance Chris traveled, their total distance should be 115 miles. So that means in this case, the two values for the distances should add up to 115 miles. So my equation is going to say just that. 1.5 times r plus 10. That's the distance that Chris traveled plus the distance his parents traveled, r. That is equal to 115 miles. Now we can go ahead and begin to solve this. I can begin by multiplying by 1.5, distributing that 1.5, 1.5r plus 15 plus r equals 115. If you want, you can clear out the decimal by multiplying everything by 10. This decimal isn't too bad to work with. Even when I'm combining like terms, I have 1.5r and 1r. That's 2.5r plus 15 equals 115. And then I'll go ahead and subtract 15 from both sides. 2.5 r equals 100, and then divide by 2.5. So that means that r is equal to 40. Remember that we define r as the parent's speed, so the parent's speed was 40. We're using the same units, miles per hour. Chris's speed was 10 miles per hour faster, so Chris's speed was 50 miles per hour. I'll fill in the units here as well. Again, notice that the units for the rate is in miles per hour, the time was measured in hours, the distance was measured in miles. So it's important that those units match.